Some experts now fear the man-made earthquakes from North Korea's hydrogen bomb test could trigger an eruption of Mount Baekdu.
Deep beneath the Earth's surface, a massive and ancient force stirs to life. China's Mega Volcano, long dormant, is beginning to show signs of awakening, and experts are on edge. This is no ordinary eruption waiting to happen. With the potential to unleash catastrophic destruction, the forces at play within this massive geological beast are unlike anything we've witnessed before. But what exactly is happening beneath the ground? Why is this volcano so unique, and what could its eruption mean for the world? Join us as we explore the terrifying truth behind China's slumbering volcano and its unprecedented power. Mount Baekdu's eruption. Rising on the border between China and North Korea, a massive natural wonder towers over the landscape. A mighty volcano called Mount Baekdu, or Changbai Mountain in China. This giant, mostly hidden from the public eye, is one of the most awe-inspiring and mysterious volcanoes on Earth. At its peak, it holds an enormous caldera, a giant crater lake that spans almost 20 square kilometers. This incredible depression was formed by one of the largest and most catastrophic eruptions in human history, which occurred nearly 1,000 years ago. The eruption of Mount Baekdu was so powerful that it released an enormous blast, classified as a super-colossal eruption with a magnitude of 7 on the Volcanic Explosivity Index. More than 100 cubic kilometers of volcanic material were ejected, with ash clouds traveling over 1,200 kilometers, reaching northern Japan and burying villages in thick layers of ash. Despite its massive scale and destructive past, the volcano remained a mystery for centuries, puzzling scientists who tried to uncover its origins. What makes Mount Baekdu even more puzzling is its location. Unlike most volcanoes, which are found along tectonic plate boundaries, Mount Baekdu sits in an unexpected place, far from these fault lines that typically shape volcanic activity. To understand how it came to be, one must first explore how volcanoes generally form. The Pacific Ocean, for example, is home to a ring of fire, a chain of volcanoes that marks the boundaries of tectonic plates. This ring is no accident. Most volcanic activity occurs along subduction zones, where oceanic plates dive beneath continental plates, creating extreme heat and pressure. Japan is a prime example of this phenomenon, as it lies at the intersection of several tectonic plates, creating over 100 active volcanoes across the region. At the heart of this volcanic process is a surprising yet vital factor: water. When oceanic crust is forced into the Earth's mantle, it carries vast amounts of water trapped inside minerals. Under intense heat and pressure, this water is released, lowering the melting point of surrounding rocks, which in turn triggers the formation of magma. This is the driving force behind the continuous volcanic activity around the Pacific Rim. But Mount Baekdu stands apart. Isolated from these tectonic plate boundaries, it challenges the traditional explanations of volcanic formation. To unravel the mystery of Mount Baekdu, one must dig deep into the Earth's geology, where hidden forces shape the land, create mountains, and occasionally unleash eruptions so powerful that they change the course of history forever. Deep beneath the Earth's surface, around 120 kilometers below, powerful geological forces set off a dramatic process. The intense heat and pressure down there change the very makeup of the rocks, forcing water trapped in the crust to escape into the layer above, the mantle. As this water seeps into the solid rock around it, it disrupts the rock's rigid structure, making it weaker and lowering its melting point. It's similar to how salt makes ice melt more easily. This shift leads to the creation of magma, which slowly rises through the Earth's layers, gathering in massive underground chambers. Eventually, this magma forces its way to the surface in violent volcanic eruptions. This ongoing process gives rise to volcanic arcs, chains of volcanoes that form along the edges of colliding tectonic plates, creating a fiery boundary where land and oceans meet. This pattern is clear, stretching all across the Pacific region, from the islands of Indonesia to the towering mountains of Chile. In fact, about 80% of the world's active volcanoes are aligned with these subduction zones, which is why the Pacific region is known as the Ring of Fire. What if the source of this activity wasn't drifting at all? Instead, what if the ocean floor itself is shifting above a stationary hotspot? Let's explore and uncover the mystery. Hawaiian hotspot theory. Beneath the vast, unexplored depths of the ocean, where the sea stretches endlessly across the horizon, a remarkable pattern quietly emerges. Following a sweeping arc of islands that make up the Hawaiian archipelago and stretching nearly 6,000 kilometers northwest, we find a trail of volcanic remnants that silently marks the ocean floor. This long chain, known as the Hawaiian Emperor Seamount Chain, is like a series of footprints etched into stone, each one telling a story of Earth's shifting crust over millions of years. At first glance, it might appear as if the volcanic activity in Hawaii is moving slowly across the Pacific, leaving behind a fiery trail of islands. But a different perspective suggests a much more fascinating explanation. This groundbreaking idea emerged in the 1960s thanks to the work of Canadian geologist John Tuzo Wilson. He proposed that the isolated volcanoes we see today weren't formed by subduction, as many scientists had believed, but by a stationary plume of molten rock rising from deep within the Earth's mantle. As the Pacific plate slowly drifts northwest, it passes over this intense hotspot, creating one volcanic island after another. Over time, each island is eroded by the forces of nature, only to be replaced by a new one in an ongoing cycle. These islands, unlike those created by plate tectonics, come from far deeper within the Earth, revealing a hidden mechanism that reshapes the planet independently of plate movements, island by island, and eruption by eruption. This theory, known as the mantle plume model, offered a revolutionary explanation for volcanoes that didn't fit the usual plate tectonic patterns. These isolated volcanic hotspots, such as the ones that form the Hawaiian Islands, were thought to be fueled by enormous columns of searing mantle rock, rising from as deep as 2,900 kilometers beneath the Earth's surface. The driving force behind this volcanic activity was a massive heat exchange at the boundary between the planet's core and mantle. Though this idea was initially considered speculative, technological advancements in the decades that followed provided strong evidence to support it. What had once been a daring hypothesis was now a compelling answer to the mystery of intraplate volcanism. It helped explain not only the fiery landscapes of Hawaii, but also the volcanic activity seen in places like Yellowstone and Northeast Asia. However, not all volcanoes fit this model. One notable exception is Mount Pektu. For much of the 20th century, the mystery surrounding Mount Pektu went largely unexplored. Its remote location, sitting at the border of two politically sensitive nations in Asia, made it nearly impossible for scientists to study. It wasn't until China began opening up in the 1980s and 1990s that international scientific collaboration started to unravel the secrets of this elusive peak. Even then, significant progress in understanding its origins didn't come until the late 1990s, when the first permanent seismographs were installed on the Chinese side of the mountain. This was a major milestone, as seismic monitoring had become one of the most powerful tools in Earth science. The breakthrough came with seismic tomography, a technique that revolutionized the way scientists study the Earth's interior. Just as medical CT scans allow doctors to look inside the human body without surgery, seismic tomography uses the behavior of seismic waves from earthquakes to explore the planet's deep structures. These waves travel at different speeds depending on factors like temperature, density, and the state of the rocks they pass through. By measuring how long it takes for these waves to reach different locations around the globe, geologists can create detailed images of the Earth's interior, uncovering structures that lie hundreds or even thousands of kilometers below the surface. Earth's volcanic mystery. For years, scientists believed they had finally uncovered the grand design behind Earth's fiery activity. They could now see how massive slabs of the planet's crust sank deep into the mantle, how fresh ocean floor emerged from molten rock beneath mid-ocean ridges, and how towering columns of heat surged upward from the Earth's core to create volcanic hotspots like those in Hawaii and Yellowstone. Everything seemed to fit together into one beautifully interconnected model, one that could explain every type of volcanic activity on Earth. Subduction-driven eruptions, deep mantle plumes, and mid-ocean ridge volcanism all appeared to be pieces of a perfect geological puzzle. But that certainty didn't last long. In the late 1990s and early 2000s, scientists got their first detailed seismic images of the area beneath Mount Changbai, also known as Mount Pektu, and the results were shocking. Unlike the well-defined continuous plumes of molten rock that fueled volcanoes like those in Hawaii and Yellowstone, Mount Pektu's magma source didn't seem to stretch all the way from the deep mantle. Instead, the underground anomaly beneath the volcano appeared to stop at around 400 kilometers below the surface, far deeper than most magma sources found in subduction zones, yet nowhere near the expected depth of 2,900 kilometers for a classic mantle plume. Even more baffling was what lay beneath it. Around 600 kilometers down, scientists detected something entirely unexpected, a massive region of unusually cold, dense rock. It was as if an invisible barrier had formed, blocking the movement of molten material from below. This discovery turned existing volcanic classifications upside down. Mount Pektu, one of the largest volcanoes on Earth, didn't fit into any known category. It wasn't a traditional hotspot like Hawaii, nor did it behave like a typical subduction-driven volcano. It seemed to be something completely new. To solve this geological mystery, researchers turned their attention to the strange cold anomaly beneath the volcano. This anomaly existed in a critical layer of Earth's interior known as the mantle transition zone, a boundary between the upper and lower mantle where intense pressure forces rock into a denser, more rigid structure. This zone plays a crucial role in how material moves within the planet, acting like a semi-permeable barrier that restricts the flow of molten rock between the upper and lower mantle. The implications were staggering. Further analysis revealed that the anomaly wasn't just a random patch of cold rock. It was a buried remnant of Earth's ancient surface. Expanding their imaging scans to the east, scientists found something even more revealing. The anomaly lined up perfectly with a long subducted section of the Pacific Plate. Rather than sinking smoothly into the depths of the lower mantle, this massive slab of oceanic crust had instead hit a roadblock. It had bent, flattened out, and become trapped within the transition zone, directly beneath Mount Pektu. This discovery was groundbreaking. For years, geologists had theorized that some tectonic plates might not fully sink into the deep mantle after subduction. Instead, they could get stuck at intermediate depths, lingering in the transition zone for millions of years. Until now, this idea had been largely theoretical, but Mount Pektu provided the first real evidence that this process was happening and that it could be linked to volcanic activity in ways scientists never expected. Hidden beneath one of the world's most mysterious volcanoes was not just a source of molten rock, but an ancient relic of Earth's past, one that had reshaped our understanding of how volcanoes are born and how the planet's fiery heart continues to evolve. How could a stagnant slab trapped in the transition zone trigger volcanic eruptions far from the nearest subduction zone? Let's take a closer look. Mantle convection debate. For years, scientists have been locked in a fierce debate over the nature of mantle convection, the process by which heat from the Earth's core drives the slow churning of rock within the mantle. Some researchers argue that the upper and lower mantle operate as mostly separate systems. They believe that when sections of the Earth's crust, known as subducted slabs, sink into the mantle at subduction zones, they get stuck at a certain depth, forming a stagnant layer. Others, however, insist that mantle convection is a single, continuous process. Geologists turn to subduction zones, regions where one tectonic plate slides beneath another, to investigate how slabs of crust move within the mantle. In one particular area of the Pacific Ocean, scientists observed something unexpected. Instead of stopping at the mantle transition zone, a region between 410 and 660 kilometers beneath the Earth's surface, certain slabs of subducted oceanic crust were plunging much deeper. Seismic imaging showed that these slabs continued their descent into the lower mantle, seemingly supporting the idea of whole mantle convection. At the same time, however, studies from other subduction zones showed that some slabs did not penetrate the lower mantle. Instead, they appeared to stagnate and accumulate in the transition zone, as if they had hit an invisible barrier. This directly supported the dual-layered mantle model. To get a clearer picture, researchers turned to seismic tomography, a technique that uses earthquake waves to create images of the Earth's interior. Similar to how a CT scan allows doctors to see inside the human body, seismic tomography allows geologists to track the movement of materials deep within the planet. What they found was astonishing. Across the world, they detected nearly 100 ancient slabs that had managed to sink into the lower mantle, some reaching as deep as 2,900 kilometers, just above the Earth's core. But they also found many slabs that had stalled at the transition zone, seemingly unable to break through. Most volcanoes on Earth are found near tectonic plate boundaries. This makes sense because subduction zones, where one plate sinks beneath another, produce intense heat and pressure. melting rock and creating magma that rises to the surface. But there are some volcanoes, called intraplate volcanoes, that appear in the middle of tectonic plates, hundreds or even thousands of miles away from the nearest subduction zone. A striking example of this phenomenon is Mount Changbai, also known as Mount Paektu, a massive volcano on the border between China and North Korea. This volcano is located far from any active plate boundary, yet it has produced some of the most powerful eruptions in history. Seismic studies of the region revealed something unusual. Deep beneath Mount Changbai, at a depth of about 600 kilometers, scientists detected a cold, dense structure that didn't match the surrounding mantle material. This anomaly aligned precisely with the depth at which some stagnant slabs were found, suggesting a possible link between trapped slabs and unexpected volcanic activity. Scientists then looked for further clues. One surprising piece of evidence came from deep focus earthquakes, which occur at depths greater than 300 kilometers. These quakes are different from the shallow earthquakes typically caused by tectonic plate collisions. Instead, they happen in regions where subducted slabs experience extreme pressure and undergo slow internal transformations. Researchers found that deep focus earthquakes were frequently occurring beneath Mount Changbai, and remarkably, they seemed to originate near the cold, dense structure observed in seismic imaging. Could stagnant slabs in the mantle transition zone somehow contribute to volcanic activity far from plate boundaries? Let's explore further. Secrets beneath the crater. In the early 2000s, earthquakes around Mount Changbai, also known as Mount Paektu, suddenly became a cause for alarm. Scientists at the newly established Tianhan Volcano Observatory noticed a troubling spike in seismic activity beneath the mountain. At first, they detected around 10 earthquakes per month at depths of about 5 kilometers. But within a year, that number soared past 100, and in some months, it even exceeded 200. The pattern was undeniable. Something was brewing beneath the volcano, raising fears that a major eruption could be on the horizon. To understand the potential danger, scientists looked at the volcano's past. Volcanic activity in this region dates back 20 to 30 million years, coinciding with a period of intense geological change in Northeast Asia. About 2.5 million years ago, things took a dramatic turn. Molten rock from deep within the earth surged upward, leading to massive eruptions of basaltic lava. These eruptions covered nearly 10,000 square kilometers, forming a vast volcanic plateau, the largest of its kind in the region. Over time, the sheer weight of this plateau changed the way magma moved underground. Instead of rising freely to the surface, the pressure caused it to collect in a shallower magma chamber. There, the magma slowly evolved, becoming thicker and more explosive. Eventually, this built up enough force to create a towering volcanic cone that stood 4 kilometers tall. But this massive peak didn't last. Over 1 million years, it grew until, in 946 CE, it was obliterated in one of the most powerful eruptions in recorded history, the Millennium Eruption. This cataclysmic blast ripped the top off the mountain, creating the massive crater, or caldera, that we see today. The explosion sent ash 25 kilometers into the sky and covered 350,000 square kilometers in volcanic debris, an area larger than the Korean peninsula. Superheated pyroclastic flows, deadly waves of gas and rock, incinerated everything within 50 kilometers, covering an area roughly the size of modern Tokyo. If such an eruption were to happen today, the devastation would be unimaginable. Despite the alarming increase in earthquakes, the volcano unexpectedly calmed down in 2005, with seismic activity returning to pre-2002 levels. However, the forces beneath the mountain are still active, meaning another eruption is just a matter of time. This growing concern has sparked international scientific collaboration. Even North Korea, usually secretive, allowed Western researchers to help monitor the volcano's activity. Using advanced seismic imaging, scientists have uncovered the hidden forces fueling Mount Paektu. Deep beneath East Asia, the Pacific plate is slowly sinking under the continent at a shallow angle before flattening out. This movement has created a massive underground reservoir of molten rock known as the Big Mantle Wedge. A break in the plate at 35 degrees latitude has allowed deep earth processes to interact with surface tectonics, further fueling volcanic activity. What makes this volcano even more unusual is the role of water. The mantle transition zone beneath Northeast Asia is packed with water, trapped over millions of years by the subducting Pacific plate. As the plate sinks, dehydration releases this water, which then fuels the formation of magma, ultimately driving eruptions. This process isn't unique to Mount Pektu. Scientists believe similar mechanisms have shaped other volcanic fields across East Asia. What do you think about the sudden awakening of China's mega volcano? Let us know your answer in the comments section. Don't forget to like and subscribe.